So basically now we have established that if we want to hunt ET, most likely we need to go outside of our solar system. So we need to find planets around other stars. Science fiction always knew they are there, but the scientific confirmation came only October 1995. Not too old, less than 30 years ago. And there are three methods that we can use. Method 2, I don't know if it has ever been used. Method 3, which will be the photometry. If a planet moves in front of the sun, of course, it will darken it a bit, which is nowadays the most commonly used, has only been allowed to do because we got now cameras that are very sensitive to these small changes in light they get from a distant object. And these were the so-called CCD cameras. So only this technological advance made it possible. But the first planets were found with the brute force method. And the brute force method, so share screen. No, wrong button, sorry. Up. Almost there. Okay. Ready. So the brute force method is the radial velocity method. And this is based like when you dance or when you have a child. What one likes to do is child grab them by the head and then whirl them around. What effectively happens, one pulls, of course, on their arms, but they also pull on you. And the same is true if the Earth moves around the sun. Of course, the gravity that keeps the Earth on its orbit is coming from the sun. But in the same way, the Earth is, with the same force, the Earth is pulling on the sun. It's just that the sun is much more massive, has a bigger mass, is much more inert, doesn't like to move that much. But nevertheless, also the sun is dancing a bit around the common center of gravity. So if we have a planet, here the blue stuff, and the star, then their movement is that basically they dance around this common center of gravity. So if the star or planet moves here, the star needs to move a bit in the other direction. But means also that the star is wobbling a bit. Of course, when will this effect be more pronounced? When the gravity that the planet acts on the star is bigger. So which planet in our solar system will have the biggest effect in terms of mass? It's clearly Jupiter. From the gas giant is the one that is closest. And it has by far the highest mass. So gravitational law scales with the mass of the planet, but then also, of course, with the distance, that this effect is more pronounced. And now if we observe from the Earth, that would be here, what happens? The star is moving away from us. Aha. The light that is emitted by the star is moving away. What will happen? Doppler effect. The same as the ambulance, when it drives away from us, we hear that the siren, now the sound, is going to be a bit deeper because the wavelength is going to be expanded, redshifted. Well, then when it's furthest away from us, there is no velocity component, which is always perpendicular to the orbit relative towards us. So the light will come unshifted, but then when it starts moving towards us again, the wavelength gets contracted, we get a blue shift, we get a higher frequency, we get the light blue shifted slightly. And this should happen, of course, periodically, depending on the orbital period of the planet around the star. So this is the brute force method, using basically this Doppler shift of the spectral lines that come from the star. Which one is shifting here? These are all the same. Here, this one seems to be shifting relative towards the other. Or they all shift a bit. You see here the position of, it's here relatively in the green, almost in the yellowish, back to the green, very deep into the green. So we can look at the spectral light. What we need is basically a telescope, which we can nicely focus on a nearby star. And then we look at this Fraunhofer lights coming from the star. We split up then the light again in its spectrum and its colors. Pick out maybe what would, this looks like helium, the spectrum of helium. Look there at the spectral lights and what happens to them with time. And plot this basically. The position of one of these spectral lights, or we can do this for all, and we get even less because we have now basically a series of experiments. We reduce the errors. How is the shift over time? This was done by some French lads in a relatively small telescope, somewhere in the how is it called? The Auvergne, but it's south of Paris, south east of Paris. What they found around the star, 51 Pegasi. So somewhere Pegasus, and one of the stars, 51's brightest in Pegasus, which is not that far away. I think it's only 50 light years away from the Earth. They have basically found such a periodic signal. And then October 1995, the first scientific publication came out that these two French lads that meanwhile have the Nobel Prize observed there a body that is very likely half the size of Jupiter with an orbital period of only 4 days. So very close towards the star, half the, so quite a big one. Obviously, this effect is more pronounced the bigger. And then you don't want something that needs 50 years, because then the time shift, relative, if you plot it over time, there's almost no period to see. You might see something, but you don't see it periodically. So you want something that is close, Kepler's law, then the period length is relatively short. And you see it basically nice, a sinusoidal curve. Of course, the condition must be the line of sight. So the observer must be the same as the plane, orbital plane, or it's best if you're in the orbital plane. The effect is less and less pronounced, and then vanishes when you look 90 degrees onto this plane. It's a very important thing. From where do you observe? What do you see at all? It's like with the galaxies. You see from the side and you see basically just a line. Or do you look from the top and you nicely see this disk? And we want now to see basically from the side. So obviously that this is a method that prefers to have the big ones very close. It was quite a sensation because so close to the star, the temperature is a surface temperature is 1000 degrees Celsius. It needs to be very big because otherwise all this gas is quickly evaporated. So it's unlikely that this gas giant has formed so close to the. But if we want to learn more about our solar system, we need to observe the others, what is there. But we also need to kick in there are these boundaries of our observations. What do they deliver? Will we find something that is Mercury size of this with this method? Very unlikely, because the wobbling is very likely of this light, the Doppler shift, so the frequency or the wavelengths over time, that might be not enough sufficient. So we have to be very careful what we learned from there, because this is obviously very extreme. And here you see the velocity. So using already this Doppler shift, this relatively change of the wavelengths over time. And this must be now some different planet. Well, what you see clearly here, some sinusoidal, one can nicely fit in a sinusoidal, especially then with time you of course go to a better observatory and you get certainly the beam time when you come along and show already the previous results that there were 2 prolonged periods of observation. And obviously you improve your instruments, etc. So your signal quality gets better, error bars get smaller, and they were probably lucky to have observed here, because otherwise if they would have observed here again, then it looks a bit like there is not really a signal. But here we start to see this sinusoidal. So this was something different from PGA-CB, because this was just half of 4 days orbit period. So it must be already further away, because we see now the orbital period is already a couple of years. Couple of years, this means a couple of astronomical units away. So, but nevertheless, this is the brute force method. You see here the mass is 2.41 Jupiter masses. Okay. Oh, the method looking at the spectral line and their shift and see whether it's periodical over time. The other method, the second method that is nowadays proposed to see even smaller ones. But here we again, the problem is if we have a foreground star and a background star. And now if the foreground star moves here past, it might cause gravitational lensing, what means the light that would otherwise pass the Earth is now also gravitational lensed towards the Earth. That would give us a light curve like this. If you see a no planet, and it must be, of course, that just in the right plane, that it also moves in front of this background star, it might cause then here a little spike while it's moving in front of the background star. That is called gravitational microlensing. The light itself that would be observed from the background star or the combined system. Yeah. I wonder whether there have been already 1 or 2 planets been reported with this method. So exoplanets. I'm not so sure. What is more commonly used nowadays, but there we need almost to go into star. So this method should be small, very sensitive even to small ones, but you need a foreground star, you need a background star. They need just to be coincide. And then you need to plan it just to be in the right, that it also moves. Yeah. How often is this the case? Good, given enough stars, there might be a couple of cases. Yet, nowadays, what is used is the transient photometry and perhaps even spectroscopy methods. Okay, what do we have there? Well, we have the situation, the planet is next or behind the star, and we get the full star. Plus, of course, the star shines towards the planet adds a bit towards the light. So the reflected light that comes also from the planet. But now, when the planet is in front of, it might block a bit of light. And then we lose a bit of the light. But then you imagine you have Jupiter moving in front of the sun. And you see this from 50 light years away. So you go park your car down in Carlisle. You leave the light on. You can even make the one that looks towards distant. You come back home to Glasgow, you go on the high enough tower that you can, with the Earth's curvature, we are not flat. You take a telescope to look at your lights, and then you see a globe in front of, or a fly going in front of the light. But then you try to fiddle out this really, because it's now a bit less bright. So if we have this darkening out by Jupiter size of planet, so if we would renormalize that the luminosity is 1, that is from A and B, in this time where it's in front of, oops, you see here it's 0.990. This means 1/1000 of the light is now missing. That would be Jupiter light. Yeah. You need to measure relatively fine. If you want to see such an effect, you need to be very fine. You need to be precise. You need to be sure this is not the atmosphere and the wind above you. So best you take a satellite. If you want to have Jupiter, so Jupiter is 11.2 times the Earth's radius, so Neptune is 4 times roughly the Earth's radius. So you see, this is basically 1/10,000. And it's blocked away. If we have Earth-like, that's almost immeasurable. It's very, very tough to say. So, yeah. Then, of course, you see how long it's blocked out. You see how often this happens. But of course, if you want to observe it if you have a limited observation time of 3 or 4 years, what will you see? Will you see Jupiter with its, don't know how long the orbital period is, 100 years? So again, if you want to have the orbital period also, it will be again planets that are relatively close. So maybe 2 astronomical units away. Again, your method is relatively unsensitive. Or unsensitive for solar systems like our own solar system. Your method prefers again the big ones. Coming to Earth, at some point there is a sensitivity limit where you cannot say anything anymore. Yet the good thing is, in these methods, when you have you have basic, where you have basically the stuff now coming only, this would be B, A and B, only from the star. So the blackening away effect so if you have now the light coming from both, what will happen if you make if you have the light coming also from the planet reflected? You will get the reflection of all the spectral lines, except if there is a capital element that has just their spectral line. It will be used to be excited, then it will irradiate the light into a different direction. So this is missing. You will get absorption lines, missing lines. Usually you wouldn't see this because, again, you are so filled with light that you don't see such a small effect. But what you can do is, if you have only the star, you take the light only from the star and subtract it. And then from this massive field, you come down to just a difference. And in this difference, you might, in the spectrum, see the spectral lines of the missing stuff. And then you can look, what type of spectral lines do we have there? Here, this looks to be yellow, and yellow that looks like sodium. Or the sodium D lines, the white mice of atomic physics. Then we would know this atmosphere has sodium vapor in it. Yellow sounds then also like sulfur, could also be there. Oh. Of course, interesting it will be oxygen or water. Oxygen. Oxygen will be very, very interesting. Why? So O2 molecule. Why is this interesting? Well, oxygen, free oxygen is only there. That oxygen is not in the water because there's much more hydrogen around the channel, or in rust, or oxygen likes to react with other stuff. It will be always bound in something else, except there are plants that have discovered the photosynthesis. And then we can produce oxygen to such a degree that there is non-reacted oxygen around. And then we know there is plant life. Yet the interesting stuff is, or if this is here, the wavelengths micrometer. Infrared micrometer, or nanometer would be shorter wavelengths, 400 to 700 is what we see. If we go then to the infrared, there it starts to become more interesting. This is when you have molecules like carbon dioxide, for example. The electrons will more sit at the oxygen at the edges and less at the carbon. Therefore, you have negative plus negative charge. And now if we can somehow bring the carbon to one side, this is like when you have two springs in between. Then you shift the middle mass towards one side, then you let bounce it, then you get vibrations. And this type of degree of freedom of molecules is in the infrared. So if we have light waves with infrared, they have just the energy to make this vibrate. Every type of movement, this vibration now stores heat basically. This is what contributes to the greenhouse effect. If you have the water molecule and now you make this type of vibrations. Or if you have carbon dioxide with oxygen, for example, you can also have them vibrate a bit, but here you can have two modes. One is going here along and one is basically going up here. The one that I have just described is that one is stretched and the other is it. But you can now stretch basically both bonds and let them vibrate. So you have here much more type of ways you can make the molecule move, and therefore you can store more heat than just oxygen alone, O2, or nitrogen, N2. So in the moment you have these higher molecules, they have more degrees, what we call degrees of freedom, possibilities to move, and therefore the heat capacity scales directly with this degrees of freedom, number of degrees of freedom, heat capacity, which means basically the amount they can store heat capacity, is like a storage room. That's what causes the greenhouse effect if you have too much of them. If you don't have enough of carbon dioxide, which happened at some point on the Earth, it almost basically completely froze over the Earth at some point. And the poor plants that caused it, that they died because they caused a global freeze. But unfortunately, volcanoes produced again carbon dioxide. And with this carbon dioxide, well, we heated up again. And the big freeze came to an end. Thank you, volcanoes. So it's a difficult balance that we walk along. Yet, what I wanted to say is that this type of degrees of freedom, which is again very specific, the energies that it happened, and therefore the wavelengths of the light that is emitted and absorbed, is in the infrared. If we have the capability to look at such stuff, at best where we know already from the optical, there is a planet. And we know from the optical, what means the visible wavelengths between 400 and 700 nanometers, we know there is a planet, we know its the properties. Then we can look again with infrared capability, like James Webb. Then we can look now, do we find here, for example, methane mostly? Do we find water? Do we find carbon dioxide? To which degrees? Do we find maybe oxygen? So if we find pure oxygen, then we know there is plant life. This is a good place to settle over. Or, so we can even look what is the atmosphere made of. And interesting, it becomes then, if we have there molecules, if we find signatures of molecules, like carbon chloride for this tricliner, we remember, then we would think about two things that can happen. That either there's somebody doing a massive neutrino experiment, You remember this was by Davis, used to detect the neutrinos from this, and then caused this solar neutrino problem, this tricliner stuff. Or they like to have their clothes very clean. But these molecules, this carbon, whatever, chloride, can only be made technologically, can only be synthesized using technology. It isn't around in nature. Why? If it hits ozone, there is always a certain degree of ozone around, O3, oxygen radical, which is very unhealthy if you have it down here on the surface, because in your lung, free radicals are very aggressive molecules, but quite good if it's very up in the upper layer of the atmosphere, because there it filters. It's very sensitive to UV light. So it filters out the UV light and protects us. Well, and if it comes with this CCl4, this tricliner stuff, this carbon fluorides or what it were, that we released into the atmosphere, that basically killed our ozone layer. Well, what I wanted to say is that if we find this type of molecules, we know there's a technology, there is intelligent life. So basically, we have now the capability to look what is going on there. So here clearly, one would say this peak is there. Here is a bit of a peak. But this atmosphere consists of methane and carbon dioxide. And here, James Webb will be very nice. Yeah, but with this transient field method, this was done widely exploited. It was mostly Herschel and Kepler. The Kepler satellite, which is shown here. And Kepler was basically always looking at the same place in space. Between Vega and Deneb, always pointing at them. What means also it had to be constantly readjusted. This is like, because it's now in the gravitational field of the Earth, it moves around with the sun. One can bring it to the Lagrange 2 point where it's a bit more stable, but nevertheless, if you want always to look at the same point, as if you're standing on a roundabout and you look outside, and you want always to fix while you are moving, you of course need to readjust constantly. That means you need some energy, you need fuel. And unfortunately, this was only for 3 or 4 years stored, and at the L2 point you cannot, there is no gas station around, so you have very limited time to do so, to observe basically. But nevertheless, that you have a relative limited space or part of space, you of course want to look at the galactic plane, so you have most stars at once. This was basically done from Kepler, looking always this, or roughly 3,000 light years, where you still have the resolution, and it simultaneously mapped about 190,000 stars. Then comes the geometric consideration that if you want to see, you need, of course, the planet pass in front of. What means you are very limited in the amount of star systems that are really have the right line or the right line of sight. But nevertheless, if you have 190,000, is a sufficient number. And back then, a lot of publications came out. First was Kepler 22 system, which was basically this. What is quite interesting, the star is similar like our sun. So you see now here in green always the habitable zone, which is of course strongly dependent where it's found, a distance from the star, the size of the star, and therefore the luminosity of the star. How much light is coming out. And here it was basically an Earth-like planet or super Earth, which is roughly two times the size of the Earth, found in the habitable zone. If it's 2 times the size of the Earth, we would expect that, of course, that it's 8 times the mass. If it's the same density, r to the power of 3, then the factor of 2 would make 2 to the 3 is 8. Yet, fortunately, we are also basically twice as far away from the center. Now gravity goes with 1 over r squared, which means a factor of 4, which means the gravity on the surface would be only twice. It's if I place myself on the scale, it's at here roughly 100 kilograms, there it would be 200 kilograms. It's still acceptable. But with time, we would all grow shorter and a bit more wider, very likely. And it was found basically in the nearby where the Venus is now slightly inside, where already greenhouse effect happens and then it can never be reverted. That happened to Venus. But very close to basically relative to Venus's orbit. But nevertheless, still habitable zone. Only twice the size of Earth. Of course, if you publish such a stuff, the evening it's in the news. Nevertheless, settling there would be, well, it would be quite comfortable because then you are still very far away from the star, which means all this tidal locking, that didn't happen. Well, better was then April 2014, the Kepler 186 system, and there the planet with the name F. So the star is A, then the next one is B, C, D, E, planet F. Wow, that is almost in the habitable zone, Mars-like. And it was really almost one-to-one Earth-like. The problem is, you see here that the star is much smaller, so almost tendency towards a red dwarf. Therefore, everything is closer towards the star. Half the solar mass, it is 11 billion years old. That means it's a first or second generation star. It has only half the metallicity of our sun. So I wonder a bit that there can be then at least 5 planets, maybe even more. And this one, even Earth size, it's a bit, because you have only half the material available of the heavy material. So nevertheless, we had the proof there are other planets the same size as the Earth, and they can be in habitable zone. So you're coming closer. And then looking here, basically this field that was covered by the cameras of Kepler Space Telescope, looking what type of planets were found, the giant planet size of 6 to 22 Earth, Neptune size 2 to 6 times the Earth size. So radius, not mass. Then super Earth size, 1.25 to 2 times the size of the Earth, and then Earth-sized planets. And you see where they were found, and quite a lot. And here's now a nice film, but we have again to consider, is this method, if we want to extract orbital periods, it must be all very close. The most stars are anyway smaller than our sun, so their planets need to be closer. Otherwise, they are gravitationally less bound. Oh. So if you click here on, then you will come to where you see basically the properties and sizes of the planets that have been observed of the solar systems in comparison to, you see that the big circles, this is our solar system that has been observed by Kepler. And after this film, you're probably hypnotized and I can tell you whatever I want. So I would say you stop now this video and then copy this link over, or if you have the PowerPoint downloaded, you can just click on it and it should automatically open. And enjoy this video. And once you've finished, just continue with this video. Okay. So hopefully you have now tuned in again. So Kepler has obviously delivered us a lot of information, both quite nice. Of course, for us, it's from this module, it became clear that the sun, so at latest in 1.5 billion years, it becomes very uncomfortable on Earth because the CNO cycle, remember, this carbon is used as catalyst for the hydrogen burning. And since there is slightly more carbon produced, it will be increased in fraction and increases therefore the energy output of our sun, and our habitable zone is shifting outwards. Then at latest in 4 billion years, when the sun becomes a red giant, it becomes very uncomfortable. So at some point we should think about finding us a new planet. To resettle. And then we, of course, want something that is nearby. Then you don't want to have the next couple of move somewhere, then in 2 billion years we need to go again. So we want to have a bit of more permanent solution. And there was a Belgian group that found basically this TRAPPIST system. It's a red dwarf. So if the size of compared to our solar system, the size of this star system is here, red dwarf, and then we find E, F, G, especially this F. This is basically Earth-like. Three planets in the habitable zone. One is basically really nice. Nicely in the center, so it's perfect. So 3 planets we could choose from if we resettle there. Well, why is it called TRAPPIST? This was found by a group from the University of Liège, Belgium, TRAPPIST. This is the special type of beer they like to drink. I have to say, for me, it's too tough. 10% beer, that is too much. But I remember I was previously talking about this volcano disaster. When this was unfolding, we were at a meeting in Leuven, nearby Brussels, which is a beautiful town. I just can recommend you. If you ever come to Belgium, Leuven, Ghent, Antwerp, beautiful towns. Bruges. Then, let's say, in the evening, back then I was younger, we younger people all went out, and it was quite all out, but out of bounds. And then the next day we realized basically they closed the airspace. And we were trapped in Belgium, and everybody was super hangover. Well, for me, it was not too bad. I had a friend just over the German border, so made it by train to Germany, and then I stayed a couple of days with my mate, which means more booze, until I made it to the Channel Coast and then took a ferry over. So not too bad. A friend of mine, he's from central Finland. He had to travel back to central Finland from via train and buses and whatever. Took him 3 days. Poor Thomas. By the way, Thomas used to play for Lodi. So enough now. So Trappist beer and its terrible consequences. And you don't want to be trapped on the continent then with a massive hangover from this terrible beer. Or much too strong of beer. Okay, Trappist system. Only 40 light years away. That might be a good place to resettle then. Of course, the star has only a 12th of the solar mass. So if you look at the Hertzsprung-Russell diagram, 12th of the solar mass, our sun here, up half, 0.1 down here. If this is 10 to the 11 years, this means 100 billion years. Down here, we would expect that the star lives for about 12 trillion years. The trillion years. Oh, that's perfect. Oh, we settled there, that's it. And let happen to the universe, whatever will happen. But this is basically the perfect home to go there. The age of this star is only 3 to 8 billion years. Well, our sun will live for 10 billion years, just to remind you. So we are now half time. Another good thing, this star, this TRAPPIST-1, has the same metallicity as our sun. We find the same amount of iron, oxygen, whatever stuff. The only problem is the habitable zone is so close to the central star. Even if it's small, tidal forces are enormous. Okay, what means rotation around the body intrinsic axis and revolution around the central star have already been locked. What means these planets always show the same side towards their star. Always the same side gets heated up. It's very warm. While the other side, the dark side, is obviously very cold. Oh, and what happens if in an atmosphere is a big gradient between warm, where the air expands and tends to go upwards, and the cold, where the air is then more compressed and turns more downwards? Exactly. The compressed air, because the air pressure is higher, presses then over here. And this causes a circle, convective currents to emerge. And the more the temperature gradient, or the difference between the two temperatures, the faster the process is going. It means we would get in this zones where we have basically the nice temperatures where we could live in this circle. We get there massive winds going. So it would be very, very uncomfortable. So not really a nice place to live. What again would give us rather the tendency to, if we look for a second home, look for a similar planet at a similar position in the habitable zone, a star maybe a bit smaller than the sun, but so that the planet can be far away, that we don't have this type of, you don't want to live constantly with a hurricane-like winds going over your head. So, of course, this would mean that we move there, that in a couple of billion years we move on. But anyway, in a couple of billion years, what happens in 5 billion years? Andromeda is coming along, and then Milky Way and Andromeda are merging, and very likely we have then a party of star creation. But most of the gas will then be lost. And star formation will come to an end, and then anyway. But of course, these red dwarfs will be around, so we could at least settle over to them. But the conditions will be not too nice. Of course, thanks to Kepler, we were now relatively good in finding planets, and here's basically the amount up to 2016, a couple of thousand of planets were known already. Thanks to Kepler, then a lot in the sub-Neptune, super Earth size, but also in the Earth size. So 200 Earth-size planets. So previously verified planets, and then by Kepler, newly verified. So previously, we see that Kepler was also very productive in this range. But we have to be very, otherwise we would have had the dominance of these giants. So now we come to a better, but of course, for the lighter planets, we need different methods. Since then, since 2016, I don't think there had been too much going on in planetary hunting. Again, because a lot of the money has been redirected for new space flights, the bringing out humans to Moon, bringing out humans to Mars, away from hunting for exoplanets. It's always where the herd is going, where's the money going? Okay, but we have heard now a lot about habitable zones, and I just want to remember you also to look for suns. There is also in our galaxy, if we take this artist impression and lay over now a ring, we will have a center of the galaxy which is too violent. Too many supernova happened. So maybe even here at the spiral rings, there where the blue stars are formed and then quickly go away at the edges, that might be also not too nice. So in the spiral arms. If we go too far out, there are not enough heavy elements. So if we look for other folks in our galaxy, yeah, they're also limited, basically, towards a range where we have enough chemical elements spread, but not too much violent events that breed these elements going on or compromise. And now I want to end basically this module by giving you what's called the Drake equation. Well, the most famous Drake is Francis Drake, of course, pirate. But there was also Frank Drake, and he basically was one of the first one to methodological look for the conditions that if there is a technology another technological civilization out there. What are the conditions? How many of them are in our Milky Way? So if one looks Star Wars, there's basically so many of them that but in reality, we know of one. So classical one-point statistics. And this trait basically looks a number of advanced technological in the Milky Way. It looks in the star formation, then the fraction of these with planetary systems, and I think it's only 15% at least that have planetary systems. So that's at the moment the number. The number of planets per system in the habitable zone gives us a feeling. If we have 200 billion stars in the Milky Way, let's say 100 billion of them are in the galactic habitable zone. 15% of them have time, so 15 is 15 billion. Let's have every 15th of them has a planet, Earth-like planet in the habitable zone. Then we have 1 billion planets. Then we can continue with the biological factors. What is the probability that there is suitable for life? And again, we need this. We need oceans that life can evolve. We need land that technology can start with high power experiments. So what is the chemical composition that we can have enough, that we can form amino acids and so on. So then comes a lot of softer factors. And then, of course, which civilizations that start evolving survive, at least survive, that discover at some point that an atomic nucleus can be split and that we can make their weapons out of. If you just, before this year, I usually have pointed out there is the Cuba crisis where mankind was very close to extinguish itself. There was the 1983 incident where mankind was very lucky not to extinguish itself. There is now another NATO threatening with the use of nuclear weapons. And at the moment, the signal I see from the invasion of Russia into Ukraine, that this wouldn't have happened if Ukraine wouldn't have given away its nuclear weapons. Russia wouldn't have dared this. The signal again from the Iraq war and from this war is, if you don't want to be bullied by the big ones, have nuclear weapons. North Korea, it's untouched. It's a shitty system, and nobody dares. So at the moment, I'm really a bit pessimistic in this way. Of course, if nuclear war, when there are 5 nuclear weapons dropped, we have seen more than 1,000 nuclear weapons tested since 1945. But the full scale, that would be. So this 1983 incident is very, very scary. NATO had an exercise where a lot of the political leaders went then to the bunkers, special bunkers which were made for the elites to survive a year longer or so. So complete useless, but they were made so that they could feel safe. Now, the Russians had just made a new early warning system. And then the early warning system showed a light flash that would be associated with the start of an intercontinental rocket. So there were anyway, the Russians were on very high alert, and then the early warning system says, there's something going on. These were satellites that were looking for these light flashes. The guy who was in charge tried to get his superior, but the superior was drunk. He tried to contact them above and couldn't reach anybody. So it was on him to make the decision, follow the orders, and immediately hammer back what he has. Or wait until this rocket would come into the radar signals of the Russian second early warning system. So you had the satellites looking for these light flashes, you had the radar. And then the early warning system showed him more of these flashes. So if there's one rocket coming, that might be just an accident. If there are 2, 3, 4, if there are 50 coming, you know, it's a full-scale attack. There were then more flashes coming. And it took 10 to 15 minutes to wait whether the radar signal would come or not. And this 10-15 minutes made the difference. You get your own rockets out, or you are basically sitting on the toilet with the pants down. You can imagine what pressure was on this guy, especially you know what happened back then to people in Russia that didn't follow orders, that showed initiative, that made mistakes. Russians never make mistakes. At least they would never admit it, because if you admitted an error, you resettled to Siberia. So this guy withstood the pressure. Until then, the rockets should have had the radar signal, and there was nothing. It turned later out that this early warning system had a fault. Every time there was a certain angle, when the sun was rising, it made similar reflections or light flashes when reflecting the light at a certain angle on the atmosphere. If there would be a more trigger happy guy being in charge, or the guy in front in the next high up in the command chain would have just said, okay, this is the signal, let's go, let's hammer out what we have. So we are back now to the situation a bit. So nevertheless, the Drake equation. So and the next thing, if we want to communicate, with how many of them could we communicate? We basically pollute space around the Earth since 150 years with radio waves. It means in a circle of 150 light years away, people can detect our radio programs. And nowadays also TV programs. They can detect we are around. So one has to also to think, if at latest when you want to see, when you want direct proof there is somebody, there's a very narrow time window, 150 years compared to 13 billion years. The relative fractions we can communicate is not that long. But then we might have even extinguished ourselves. But these factors enter the Drake equation, which makes then an estimate for the number of technological civilization. Yet, I would stay with a conservative estimate. This is, we have one in the Milky Way, and that's the one we should care about. and not how the guys in Vega are doing. It's rather how we are doing. What are we doing with our planet? And hopefully, after this module, you will be more grateful to all these little random circumstances, like having the right reaction rates for two protons to fuse in our sun, that our sun can do this for billions of years. And just with the right amount, that we get the right amount, that we have liquid water. That the early solar system, they are crashed into our Earth and created our moon. So we have a magnetic field, we have water left. Oh, all these small circumstances that made us so lucky that we basically could do this module, and hopefully you also enjoyed it a bit. And hopefully you will successfully continue your studies. Oh. Okay, I think that was it for this module. And thank you for your engagement in this module. That's what I wanted to say. Then see you, at least some of you, later stages in probably 2 years for atomic physics. Bye.